you, Team 12, for being here. We're really excited to see your final project and where you all have come since last semester. So just to reiterate, your presentation should be around 7 minutes, your video 10-ish, and then the last portion of the 30 minutes will be Q&A.
Yeah.
Is only one of you sharing your screen for the presentation?
Yeah, I can share my screen.
Awesome.
Oh, it says host disabled attendee screen sharing.
That's awkward. Okay, can you try now?
Yep. Okay, I think it's working now. Okay.
Awesome.
Present. Oops, sorry. Just gonna go back to the first slide. There we go.
Awesome. So whenever you're ready, we can start.
Great. Well, good afternoon. We are AutoGreens. We are an interdepartmental senior design group with students studying computer engineering, electrical engineering, and bioengineering. We spent the past couple semesters working on a product to address the inaccessibility to food, healthy foods in the United States particularly. So today we are in crisis mode and food is of concern. We were originally inspired by this idea of food deserts where there's limited access to fresh produce, particularly in the United States, as you can sort of see these maps on the right. Before the COVID-19 outbreak, upwards of 13.5 million people lived in food deserts in the United States. But today, amid this crisis, there are concerns with quarantine prep, emptying the shelves. There's fewer workers in the fields and in grocery stores, which means that there's less availability of fresh produce. And this also translates to there may be concerns with spoilage and trust in handling. So our product serves an unmet need. We use microgreens as our model plant. These are young vegetable greens that they're very highly nutritious. They can be harvested within 2 weeks. They're small and they can be grown indoors. So our aim was to create a product that would have an automated microgreen cultivation and harvesting system. And this serves the needs for microgreen facilities, restaurants that want to grow their own fresh produce in-house, individuals and community centers who want to educate people on growing their own food. Now I'd like to pass it off to Jackie, who will talk more about the overview of our product.
Thanks, Melanie. So first, we have a 3D printer base upon which our microgreen growth tray, which houses our microgreens, rests. This is the first version of our growth tray, and here you can see the microgreens growing in it. Here's version 2 of our growth tray. The growth tray also houses the microgreen growth pads, which replaces the need for soil. We're using a Raspberry Pi as a microcontroller, and it's attached to a pump system which pumps fertilizer and water to the growing pad, which wets the pads and provides nutrients to the plants. We're also controlling an LED growth light with the Raspberry Pi. This provides energy to the plants. And we're using a hair clipper to harvest the microgreens, controlled by the Raspberry Pi. Finally, we have an Intel camera taking pictures of the microgreens. It sends the information to the Raspberry Pi. An image recognition algorithm detects whether or not the microgreens are ready to be harvested. And when they're ready, the 3D printer lifts up the growth tray and the hair clipper cuts the microgreens. Now I'm going to be passing it back to Melanie to talk about the specifications for our project.
Thanks, Jackie. So the specs for completing this project included automating the plant cultivation system, controlling the water input and light accessibility. We wanted to automate the harvesting, especially reduce the harvesting time by 50% compared to manual harvest. Next, we wanted a computer vision system that could correctly predict the harvest time using a binary classifier of whether or not to harvest. In terms of the growth tray requirements, we wanted to fit on a 3D printer stage and have uniform seed dispersal throughout. The blade required safety concerns, but also we wanted it to be able to cut the plants efficiently and effectively. And lastly, there were ethical considerations, especially with the camera usage of the Intel camera, data privacy, the nutrients, biosafety that's being fed into the system, as well as the proximity to the automatic blade to the user. Now Lena's going to talk more about the growth tray.
One area of innovation in our project was in our growth tray. So in phase 1, we wanted to create a housing system for the growing microgreens, in addition to creating a layer to be a guide for cutting our microgreens. Then in our phase 2, we implemented our irrigation system and housed this under the growing tray so that when water was pumped through, it would directly hit the growing pad and the roots of the microgreens. And then finally in phase 3, after completing some growing trials, we realized that it was difficult to plant the seeds into the tray, so we made our levels slidable so that we could easily place and plant the seeds in our tray. In addition, we began working on a controllable lid so that we could adjust the humidity of the microgreens. Now I'm going to pass it on to Jackie and Ben to talk about harvesting.
So for our harvest readiness detection system, we're using IBM's image recognition algorithm. On day 1, we plant the seeds. On day 7, the algorithm returns tags. But we see here there's no tags related to plants. On day 8, when the greens are more mature, we get more plant-related tags. And then on day 15, we get tags like salad greens and leafy vegetable, so we know the plants are ready to be harvested. In the future, when we have more data, we can tune this classifier more towards microgreens specifically.
So we decided on using a modified hair trimmer as our harvesting blade for its inherent safety and proven ability to harvest microgreens. This hair trimmer is controlled by a MOSFET relay circuit driven by the Raspberry Pi, which allows us to turn it on and off when we want it to be harvesting the plants. Now I will pass off to Alina, who will talk about our project timeline.
So we formed our team around this time last year, and over the summer we were working on our project concept, and we settled on this idea in September of last year. Then over the fall, we worked on gaining control of the 3D printer, in addition to our initial designs of the blade and the growth tray. And we presented all the work we accomplished on Fall Demo Day in December. After the break, we began working on our drip irrigation system, and we finalized the design of our harvest blade in addition to our growth tray. Unfortunately, due to the events of COVID-19, we were not able to complete our project, but our intended final project would have combined the pieces that we've worked on together, in addition to complete automation and a testing trial from seed to harvest. In the far future, we wanted to add things like moisture sensors, in addition to considering options for energy efficiency like solar panels, and we wanted to scale this up for more professional usage. Now I'll pass it on to Ben, who will talk about our competition.
So we believe our product represents an innovation of what's out there. Our main competitor would be Miracle-Gro's AeroGarden 12 indoor growing systems. However, our project is an innovation over these with its automatic harvesting, smart sensing, scalable nature, and larger capacity for similar costs, which is advantageous to microgreen growers who grow with vertical shelving and could use our controllable trimmer. Our project budget was $450 and the 3D printer frame costs about $200. However, we believe we would be able to deliver this between $400 and $500, which is within the price range that our industry research found that growers would be willing to pay for all of these automatic features. Now I will pass back to Alina to conclude.
We want to thank our contributors to this project, specifically Dr. Santiago, who was our advisor, and the professors to the senior design course, as well as the TAs. We also want to thank the microgreen facilities who provided us with useful information, in addition to the ESE department and the bioengineering lab to help support us in our engineering studies. Thank you for listening.